Okay, welcome back. We're now going to begin to look at how logistic regression program processes these data and how the coefficients and standard errors and so on look. So remember that we had that the odds ratio was 21 times 51 over 22 times 6, odds ratio of 8.11. So let's jump ahead in the notes a second and let's look at this on page 89. This is the STATA output for these data. Now, up at the top, I've given STATA a very powerful command. I mean, it's one command, and it says to generate a new variable called age d. This is the dichotomized version of age. And age d is equal to, and then after the equal sign, we give it a logical expression. So the logical expression says to STATA, is age greater than or equal to 55? Ask the question. If the answer is yes, age is greater than or equal to 55, then age d becomes a 1. If age is not greater than or equal to 55, then this is false statement, and so age d becomes a 0. So just with this one statement, it generates the dummy variable 0, 1 for age d. And then we go ahead and run logistic regression. We say logit chd age d, and so that puts the single variable, the dichotomized version of age, into the model, and we get this. Okay, so remember, we've just run a logistic model with a binary independent variable, and we have results. And so the first thing I would ask you is this model with age d a better model than the naive model? Now, what would the naive model be here? And again, we know that for these data, 43% of the individuals had CHD. So the naive model would be, no matter what someone's age is, no matter anything about the person, we would always estimate that their probability of CHD is 43%. Okay? Now, we want to know whether this model is a better model than the naive model. So, and what's the answer to that question? Well, the answer to the question comes from looking at the likelihood ratio test, okay, which is chi-square with 1 degree of freedom, and we have a test statistic of 18.7 and a p-value of less than 0.0001, so highly significant, which says, listen, if you're wanting to estimate the probability of coronary heart disease, you really need to know age, because age is a very important, and you don't need to know the exact age. According to this, all you need to know is whether they're greater or equal to 55. That's a very important predictor of CHD. Okay, so you have the model here. Notice that here you have the constant term. Okay, that's beta naught is minus 0.84, and beta 1 is 2.09. And so given that you now have beta naught and beta 1, you could compute for each individual in the sample, you could compute e to the beta naught plus beta 1 times either 0 or 1 over 1 plus e to the beta naught plus beta 1 times x. And that would give you the probability of CHD for each and every person in the sample. Now, there are only going to be basically 4 probabilities. There's going to be a probability of CHD if you're less than 55, and a probability of CHD if you're greater than 55, and a probability of no CHD if you're less than 55, and a probability of no CHD if you're greater than 55. That's all there is. So there's going to only be 4 values that are generated. And if after you generate this model, if you say predict, give it a name, pi hat, an estimated probability, pi hat, predict pi hat, try it when you have a chance. If you say predict pi hat, and then look at your data in the data editor, you will find that you now have a new variable called pi hat that takes on one of 4 values, depending on what someone's what someone's independent variable is, that is what their age is, and also what their CHD status is. Okay, so now the other thing you can do in STATA is you can then say logistic CHD age d. Okay, logistic. And if you say logistic, STATA runs up to this table, grabs this coefficient, exponentiates it, and produces the results down here, 8.11. So this says that the odds of CHD among individuals who are older is 8 times higher than the odds of CHD among individuals who are younger. Okay? So there it is. That's the odds ratio. It's done the work for you. It also has taken this, it's computed a confidence interval based on this log odds ratio, and here's the confidence interval for the log odds ratio. Notice that it does not contain 0. Okay, so it's very significant. And then it exponentiates both of these endpoints and comes up with a 95% confidence interval for the odds ratio. And you can see that this does not contain 1, the odds ratio. So you have all your work done for you. If you are interested in the odds ratio for a binary independent variable, you simply have to say logistic, and you have the odds ratio done for you. Okay, so again, what we've seen then is that this is the model. Again, any statistical package you use, you're going to get something similar to this. Here's the wall test statistic, and the wall test having a value of 3.96. Remember, the critical value is roughly 2. So this is way bigger than the critical value. So it's giving you pretty much the same information as the likelihood ratio test, and telling us again that age is a highly significant variable if you're interested in estimating the probability of CHD. The odds ratio, again, is e to the coefficient, 2.0935, which is 8.1, and you get the same result here. This is not luck that this is 8.1. This is algebra. I mean, we went through the algebra together, and we saw that this is just the way it is, that e to the coefficient is the odds ratio. So here we computed the odds ratio using a 2-by-2 table. We get the same result if we take e to the coefficient. Also, again, the log of the odds ratio is the log of the coefficient, 2.0935, and that's what we see here in the table for the coefficient 2.0935. And this may not seem to you to be a big deal, especially because we know how to compute a 2-by-2, we know how to compute the odds ratio from a 2-by-2 table. So you may ask, well, you know, so what? I mean, why is this important for me to know? And the answer of why it's important is that if you have a model that has more than one independent variable in it, and you take e to the coefficient of a variable like age, dichotomized age, that e to the coefficient, that odds ratio is no longer a crude odds ratio, it's an adjusted odds ratio, where the adjustment is for all of the other variables in the model simultaneously. That's a really big deal. That's a really big deal, because ordinarily, I mean, historically, if epidemiologists wanted to compute an adjusted odds ratio, they'd have to stratify the variable, they'd have to stratify the population on the basis of that variable that they wanted to control for, and they'd have to pool over the strata. And it's a lot of work. It also can run into a lot of problems with very sparse tables. In logistic regression, all you have to do is take e to the coefficient, and you get the adjusted odds ratio. Okay, so let's do this one last thing before we have a break, and I just want to talk briefly about confidence interval estimation for the odds ratio. You know, if you think about generating a confidence interval for an odds ratio, you realize that there's a problem, because odds ratios can vary between minus infinity, between 0 and plus infinity. The null value is 1. So clearly there's going to be a very long tail to the right, but it's going to, the lowest value being 0. The way epidemiologists have dealt with this is that you can't simply take the odds ratio as is and compute a confidence interval because of this lack of symmetry. So epidemiologists have traditionally built the confidence interval based on the log of the odds ratio, because that's more nearly normal. And then once you have the log of the odds ratio, again, that's beta hat 1. Beta hat 1 is the log of the odds ratio. That's approximately normally distributed, with mean the true log odds ratio and the variance of the log odds ratio. And the other kind of thing that helps us out a lot here is that it's long been known that the variance of the log of the odds ratio is, I think, a miraculous fortunate expression. It's just the reciprocal of the cell counts added up. So 1 over A plus 1 over B plus 1 over C plus 1 over D, that's the variance of the log of the odds ratio. And the standard error of the log of the odds ratio is simply the square root of the variance. So so this is a very commonly used technique. I mean, people take the log of the odds ratio plus or minus C times the standard error, exponentiate, and they get the confidence interval. Okay, so in our example, we had that the log of the odds ratio was 2.0935. The standard error of the log of the odds ratio is, again, 1 over A plus 1 over B plus 1 over C plus 1 over D, where A, B, C, D are the cell frequencies. And you add that up, you take the square root, and you get 0.5285. And so the 95% confidence interval is e to the log odds ratio, 2.0935 plus or minus 1.96 times the standard error of the log of the odds ratio. And so since you're exponentiating, you find that the odds ratio confidence interval is 2.88 to 22.86. So we build our confidence interval based on the log odds ratio, which is more normally distributed, more symmetric, and then we exponentiate and we get the confidence interval for the odds ratio. Okay? Commonly used technique. And again, this is what, this is essentially what STATA does when it gets the confidence interval. It computes the confidence interval based on the log odds ratio, and then exponentiates that and exponentiates the endpoint of the confidence interval for the log odds ratio to give us this table when you say logistic. So let's take a break, and when we come back, we're going to look at an alternative kind of coding that is somehow popular in some statistical packages, but can also be quite useful in your research. So see you after the break.